All right. So van der Waals gas is it's a beautiful equation. So it's actually, what number do I use? It's a D. Yeah, actually, it is actually a C2 van der Waals equation. And it's so important that actually they have to tell you, and then probably I'm going to continue a little bit portion on Friday's class. So van der Waals equation is nothing but just a correction of two things. What do we say about is, yeah, it should have a size, right? It should have a volume, right? So if I have draw this, if this is a volume that we can measure, but the gas molecule does have a volume, right? So what they think about it is, can we take out the volume and just looking at the volume that is not occupied by the volume? So what's that? And then there is we're going to say molar volume, and the molar volume minus certain molar volume like excluded volume effect. And so this is a van der Waals correction factor that he called it B. So this is one kind of idea. I mean, it's not really like the best idea. I think a simple idea is always good. So I think I like this idea. Simple correction on this, and that actually one step closer to the real gas. Second one is an interaction. And this is defined by A, okay? Size is defined by B. And what's that going to be? The interaction is essentially the gas molecule has to collide each other, right? So what I'm going to do is, it's going to be, for me to find the probability, this is for me to chance to find a gas molecule, one molecule, another gas molecule at the same position at the same time. So this is essentially collision probability, right? Collision probability, and then this is how effective they are. So this is some correction term is going to use, and then how these two comes together comes from here. So I'm going to write down the PV equal nRT. Okay, and then what I'm going to do is I am going to change it as a pressure is volume divided by nRT. So this is also another way. I told you in the concept about compression factor, this is a volume is supposed to happen, and as an ideal gas, and if the real volume is smaller than ideal volume, they have attractive interaction. You got that right? But the same idea is here. This is the pressure that's supposed to happen, but if the pressure is lower than it's supposed to happen, they have attractive interaction, right? So pressure can be an indication of interaction, whether the interaction is attraction or repulsion. So he arranged this idea into this way. Okay? And then this equation now has to be corrected. The easiest correction is this. Oh yeah, okay. So this is a volume, and my correction for the normal molar volume. So this is an MB. So that's the first correction of the size, right? So that's the first correction of the size. That's how there's excluded volume, and this is an easy job. Okay, and then what's going to happen is, okay, this is a pressure is supposed to happen without having attraction and repulsion. So now I'm going to put down this term, collision probability, and then multiply by A. And I'm going to correct it, and he chose to do as a negative sign. So that's a van der Waals equation. So this is essentially collision probability And then that's how effective. So it's essentially interaction constants. How the interaction is effective. So this is the van der Waals parameter A, and the parameter B is going to be used. The most common equation that people usually use is, instead of using n, they divide this one by n and both sides, and the equation now becomes pressure. This is a lot more commonly used. RT molar volume minus B minus A 1/Vn to the square. So this is the same equation, but that's the like a more widely used term. So it's very explicit and it's easy to see, and the equation is right there. So when A is positive, what kind of interaction we are talking about? When A is positive, what do you think? You have a pressure then lower than it's supposed to be happening, right? There's an idea of attraction, right? So A is in the attraction. You like this kind of correspondence? When A is positive, which is a usual case, okay? Most cases, if you bring them together, they have an attraction, and then A is positive. That's why he put this one down here in a way, in a weird negative there. Equation as a negative, because he wants the equation to be having this parameter A that he defined to describe attraction when A is positive. So therefore I choose to put a negative sign in front of this to have a correction. Okay? So it is a correction of those two. It's so beautiful. Very, very nice. Okay? One last thing, the comment that I'm going to have is this. And then now you have this equation, and it's actually pretty simple test. If you plot the molar volume as a pressure, do you guys remember this? Right? You bring it down. There's a liquid to gas condensation, and it goes up. That's the idea, right? But if I put this equation down, depending on the A and the B value, most cases you are going to have something looks like this is what you're going to have from van der Waals equation. So that's the equation that I have here. If I draw it, I'll have an equation looks like this plotted in. And let's think about this is how unrealistic it is. If I'm pressing down, pressure goes up, right? If I make a volume decrease, and what's happened here? Pressure goes down. I mean, can it ever happen? If I make the volume down, pressure go down? No, right? So that's the flaw of the van der Waals equation. This is not happening, right? That's a flaw, but it's not even flaw. Actually, this is somebody called the Maxwell Construction. What Maxwell suggested is what this van der Waals gas trying to give us is if you do this, draw the line that has the same area on both sides. This is a point at which liquid to gas condensation start to happen. So he's trying to make that this changing the curvature has a meaning, and this is not arguing that this is what it is, but when you draw the line that has the same area, this is where you can have liquid to gas condensation happens upon compression of the gas. And that's what you can do. And now you start to see this. You guys remember, okay, so when I have a higher temperature, I guess I will have something looks like that. And eventually I will have something looks like this. Critical temperature, right? this is a critical temperature. Right? Where, if you look at the curve, that's, do you see this? This point, this point, this point? Okay, actually, no, not this point. Just this point. You know this point? This is what is where the curvature is changing. And also, you see this point, where the slope is 0. So you got 3 data points, which is, if I take the derivative of this, if the slope is 0, that's this point. And if I take one more derivative, which is 2 times on the van der Waals gas, that's where the surface curvature is changing. And if I continue to do that, and this is where at the temperature is critical temperature. And you can get the mathematical prediction of A and the B based on the critical temperature. This is something that I love to close that with this statement. Where is that? Yeah, so here we go. So critical temperature is, if you do the math, this is what that means. Okay, so here, and also the critical pressure, it depends on the A and B. You guys do not have to remember this equation. But what I'm saying here is, do you think that we are measuring this? This is something that is, I think, the good thing to know. We are not measuring this. There's no way that I can measure that, right? But what I can measure is, I can measure this, critical temperature. Right? Once I measure that, I have a puzzle, one piece of the puzzle in my hand. And you can also measure the critical pressure, which is the experiment to measure. That's also a combination of A and B. And so you do 2 equations, 2 unknowns, you guys can calculate. And that's why you got the A and B value. I will start my next lecture with writing down the A and B values. But always remember, this PChem course, you measure pressure, temperature, volume. That's all you guys can do. That's pretty much all we're dealing with. And we're going to deal with something other variables and something that we're going to come to. Okay, thank you very much and have a good rest of the day.